Hey, you guys, welcome back. So today we're going to conclude the stats sub lecture series or whatever I want to call it. I keep forgetting what I actually want to call it. Um, Today we're going to talk about reliability and validity, and then we're going to add in some of these other pieces that we haven't really covered yet to make sure that we kind of give the full swath of what we're trying to understand with the statistics stuff, which is some of the questions that I've been hearing in class. I can now address some of those finally, which is how much can we trust this? When it comes to reliability, we're going to give that a definition. Same thing with validity. And what these are supposed to do is they're supposed to allow us to kind of understand where do we get this wrong? How much do we get it wrong? And can we really trust the statistical process to give us something valuable? Now, one other thing I want to say, just because of what's come up in class, is that there seems to be quite a bit of distrust about this whole process. And I want to put that into some historical context just to give a sense of where we are here. It used to be back in the, I don't know, I mean, let's just say it this way, for the past probably 200 years, if not 2,000 years, we've been telling this story of increasing reliance on science or the scientific process because we know that our individual perspectives can be, not are, but can be fallible. In other words, we sometimes get it wrong. And if we can say, well, I'm not just going to rely on my opinion, I'm going to rely on other people's opinions too. So then we develop this, well, let's come up with a guess, and then we'll have this hypothesis and we'll test it. We'll run it through some tests, and then if we verify that, then we can feel confident about the data that we have. And then we let somebody else take that same test with our same data and they reproduce it. And then we put our papers through peer review and this whole process of like hypothesis, test, theory, and that whole thing that we spend grade school learning about. It's so that we're not relying only on our own perspective, but we're relying on a systematic process and then the processes of other people reproducing the same results with the same data. That's turned into now this reliance on numbers and scientific processes. And for probably the, I don't know, 40s, 50s, 60s, 70s, there was this big reliance on we need more science, more of that process. And it became very this kind of rigid thing that we did. And then we had what I would argue is like the 60s, 70s kind of civil rights movements and all this reintroduction of humanistic principles and kind of emotional language that we're now sort of burgeoning now in our field. And we're saying, but we can't discount all that emotional stuff. And all, by the way, the problems with the systematic process, they make errors, and more importantly than making errors, they make a system of bias. And so now we're on the other side of that science saying maybe we can't trust that. And I think that's part of what we're feeling out in class. This I want to rely on this human connection, this very, I don't know if ethereal is the right word, but sort of emotional, maybe artistic, not so scientific, that kind of thing that happens between people, that it's moving this pendulum back towards we just need to feel our way through it and our own personal judgments matter. Now, that's both a good thing and a bad thing. So the story we're telling here, I'm not going to go too long into this part of the explanation, but the story we're telling here is, well, and I'm going to use this phrase because in one class it came out, I said, throw the baby out with the bathwater, which is sort of a morbid phrase, I guess. But it basically means we don't want to get rid of the science and we don't want to get rid of the reliance on other people in that systematic process. But we need to understand where we can get it wrong. And that's what this is about. Also, we need to understand the limits of our own personal fallibility and how our seeing through our own rose colored glasses can be problematic. And so we're doing that in different parts of the program. We'll continue to have that discussion as we go through this class as well. So let's jump into it. So first of all, let's get a little bit of an understanding, and this is basic, but just an understanding of what validity and reliability are. Um, excuse me, I'm already getting choked up. It's so great and wonderful to be. No, I'm kidding. I just had something in my throat. So I'm going to skip forward just a little bit here too. But validity, in short, it basically just means, are we measuring what we intend to measure? If I take out a teaspoon and I dip it into a sugar dish, I want to know that I'm getting an actual teaspoon. If I heap it over or like leave a little space in my little teaspoon, I'm not getting what I'm intended to get. So I got to use our tools correctly. That's what validity is, making sure we're measuring what we intend to measure. To give a sort of psychological or therapeutic example, if I'm trying to understand the intensity of someone's emotional experience, I want to be able to get that right. So if I say like, well, on a scale of 1 to 10, how much do you feel this? And they're like 10. And I'm like, okay, but last week you said 10 too, and it seemed different. And they're like, oh, okay, maybe it's 8 today. And so we're using our questions and sort of these informal scales to really try and get an understanding of, am I understanding your feeling or your experience accurately and correctly? We can do that in test form. We can do that through conversation, but we're trying to measure what we're supposed to be measuring. That's the idea. Reliability then is consistency or consistency of measurement. It's just like saying, uh, later on when we get to the Myers-Briggs or personality inventories. Some of you have taken these before and you're like, it kind of changes though. Does that mean it's not quality or it's not good information? And in some tests, yeah, that means that it's unreliable information. Other tests, we can expect some change to happen. So that's what we're going to talk about when we get to reliability. So let me go back here. We'll start back at the beginning. Um, Here, let's see, what do I want to read all this? I'll read this quote here because I thought this is kind of a good summary. It sums it up. As a counselor using assessment, you must be able to evaluate the argument for validity made by a test developer or researcher and determine if it is sound. In other words, there are lots of tests out there, and the responsibility falls upon you to decide, is this test a good one or is it not? Now, one of the threads throughout this course is we're talking about, do we use assessments at all? Some of you are like, no, this is stupid. Others are like, yeah, I'm starting to see the value of using the tests, which I think will build hopefully a little bit as we go through. But I'm seeing the value of using the tests. I just don't know how to tell if it's a good one or not. Can I trust anything that I find on the internet? I think in 2024, we're learning that the answer is sometimes, but maybe kind of not. But there are things that you can trust. The question is, do we know how to do that? So that's what we're going to be talking about a little bit here through this lecture. Here, below here are just some different ways of describing validity, some important points. I think I'm going to skip over that first one because we've kind of already said it, but it's, I guess I'll mention it. So validity, sometimes we use the word, is that valid, as a synonym for, is that true? And the second point here is that it's not necessarily that we're talking about, is it true or is it not true? It's a matter of degree. So how much is it true and how much is it not? Um, one of the I think maybe one of the clearer examples I can give is if anybody watches crime TV and you've seen those courtroom situations where you have an eyewitness up on some witness stand and they're like, "Did you see the masked assailant leave the store after stealing things, whatever?" And they're like, "Yes, I did. I saw him. I'm 100% sure." And you're like, "What color was his shirt?" And they're like, "Blue." And then they get another person who was an eyewitness and they're like, "No, the shirt was red." In other words, both people saw somebody and they're really certain of that, but they weren't certain of all the details, which is kind of testament to, we are fallible. Sometimes we get it wrong. Also, number two here is it's a matter of degree. How much are we getting it right and how much are we not getting it right? And we've systematically developed some processes. I keep saying processes like I'm British or something. I think I listened to too many podcasts. Processes. We have processes for determining how much are we understanding that is correct and how much is probably not correct. And there's a more formal way of saying not correct, which we'll get to. But just know that it's a matter of degree. Okay. Um, there are different kinds of validity. When we say, is it valid, as a synonym for is it true? Well, there are different kinds of truth, so to speak. In other words, we'll cover different kinds of validity and then we'll decide, well, it could be true in this sense, but not in the other sense. We'll give some more language to that. And then this is sort of a catch-all caveat that no test is valid for all purposes or all groups. In other ways, to use our hammer analogy, a hammer works in some situations, but not all situations, and not with all for all projects. You could say it that way, I guess. So that's just some general kind of starting points. If you look up validity in on the internet or in a textbook, it used to be taught in this 3C model, and it's not that way in our book. Um, we're kind of moving away from that, and there's a very important reason. There's one additional thing that I think we're considering in light of that historical trend to move from science to sort of maybe a more humanist perspective, if that language, if you'll accept that. So let's talk about the 3C models, the 3C model, and then we'll kind of say, yeah, but that's also the old news, and we're thinking about it in this new way now. So we'll start there as a starting point anyway. Um, so a construct. Let's talk about what a construct even is, because the first kind of validity we're going to talk about is construct validity. And there are number one and two here are different kinds of construct validity. One of the things I'm going to say also is just sort of another caveat is that I'm not going to go really in a deep dive into these things because, again, keeping our focus on are we using this to make good clinical decisions? In other words, if we know enough to say this test is good or I should move forward with using it even though it's not perfect, then that's probably enough. So there's a lot of like getting in the weeds of specifically the math and science of what these different kinds of things are. I'm going to try and sort of give a summary to skirt over the surface of them because I don't think we need that deep dive in order to do our work, essentially. So if you hear me saying things that are confusing, what I'm going to try and do is sum it up in a very sort of high level, easy to understand way. And if you get confused, that's okay because the deeper we go in this, the more confusing it gets. So construct. What is a construct? If I asked you what a dog is. Everybody in this room or watching this video would say, "Yeah, I kind of know what a dog is, right? Or they're furry." And I was like, what about that meowing thing over there?" And you're like, "Well, that doesn't fit my construct of a dog because it's meowing and it moves differently and it doesn't have the same sounds and it eats different food and it stays up all hours of the night walking on my face and dogs don't do that." So like there's this construct of dog, construct of cat. We also have the construct of an animal. The more we grow from birth into adulthood, the more we can refine our constructs of what certain things are. And as we're going through classes like this, we say, is this state of experience sadness? Well, it's kind of sadness, but it's also like depression, or it's not just like bummed out, it's like sad and it's like pain. When I say those words, it sort of relays this different level of intensity along with them. And what we're trying to do is understand the construct of whatever that sadness is at different degrees in different situations, different experiences, and that kind of thing. So we're refining this construct. If I going back to the dog analogy, if I say, okay, well, I'm going to build a test so that I don't have to just rely on my maybe unrefined understanding of dogginess, and I want to make a test that says, okay, I'm going to find out what a dog is. Okay, so question one: does this animal have hair? Yes. Okay. Does it have a wet, slobbery tongue and a slimy nose and does it wag its tail when you walk in a room? And we think of all those different things that describe dogginess. We would come up with a test that would differentiate a dog from a cat or some other thing. But what if I left one of those things out? What if I said, this animal, we know something about dogs, like, what's a good example? Dogs chase balls. Cats don't really chase balls. They chase stuff, but not balls, right? And I don't know another animal that like chases a ball. What if I left that out? But that was a really crucial part of understanding the nature of a dog. Then I would have this thing called construct underrepresentation. Another way to say that, kind of in summary, is if you have a test that is trying to test, we'll just use an easy one like we always do, it's trying to test depression, and I leave out one of the main symptoms of depression, like, suicidal ideation or, overeating or undereating or something like that, oversleeping, insomnia, or hypersomnia or hyposomnia. Those are all symptoms of depression. But if I had a test and I left one of those questions out, I might not be understanding something core to what depression is or to what a dog is. That's what construct underrepresentation is. So we have to have a full enough picture to understand the entire construct of what that mental thing is that we're differentiating from something else. Okay. So that's probably a good enough example. We can leave it there. Construct irrelevant variance is kind of the opposite. It's not leaving something else something out that should be there, but it's putting something in that doesn't really fit. So if we're going back to our dog and cat analogy, let's say I have a test about dog: wet nose, slobbery tongue, happy disposition, and it has fins. And you're like, well, that's kind of irrelevant. That's not what dogs have, right? That introduces variance or variability into our scientific process. So if you that word seems kind of confusing to me. So if you take out variance, if you just say there's something irrelevant in here that doesn't need to be here, that makes the test mostly good, but then it also introduces something that's not good as well. what this looks like, and I'm not going to dive too deep into the science here, but if I build this test and I'm like, okay, yeah, wet nose, slobbery tongue, and fins, and I have probably more than that, more than just these three things. But if I give this test to a bunch of people and I say, well, I have to sort of set my norms, I have to set how who this test works for and what typical or normal scores are like. That's how we get our normal curves, and then we can then give it to a client and say, well, compared to these other people, you have less dogginess, or you understand less dogginess, or something. If I do that, I'm going to find wildly different numbers when it comes to the fins as opposed to the wet nose and the slobbery tongue, because people generally know what slobbery tongues look like. And most people are like, yeah, but fins, that doesn't count. And so those numbers are going to look really different. And then I'm going to say, oh, that one doesn't really fit. So we need to take out that. In other words, we're making the test more valid by removing irrelevant things. Okay. So, like, there's sort of a systematic process to do something about this validity. Just one quick example. Another one that feels like it's kind of related, and there are very subtle differences is to why this is, but this idea of test content. So construct is the mental thing that we think about in terms of dogginess or depression or whatever. And then there's the test content. I kind of already described test content when I was talking about construct. Scientifically, they're different, but for all intents and purposes here, or practical purposes, they're kind of the same thing. And they're not. Someone's going to yell at me and be like, no, they're very different, Aaron. You can't call them the same thing. And I'll say, yeah, okay, you're right. But we don't need to know this in order to do our work. So, um, essentially, it's the relationship between what's on paper and the construct and the way we're thinking about it. So if you want to fight me on it, that's fine. I will probably concede and say you're right. It's not 100% accurate, but for our purposes here, then that's fine, whatever. The other one that's kind of important is the response process. So if I develop this test, then I say, okay, I have my dog test or my depression test, and I send it out into the world, and I say, okay, everybody write down your answers. And then there's somebody who doesn't write, doesn't know numbers, doesn't know words, can't read, speaks a different language, whatever. The process of which I'm gathering data is not getting me good data. It's just not working. So it's nothing to do with the construct. It's nothing to do with the content. It's the process itself for which I'm gathering it. So, like, if you're testing people with ADHD in a room filled with clocks, you're not gonna get good responses, right? So this is part of the justification for standardizing the space and the process and the questions. It's because if we standardize all that stuff, we can remove all of those extraneous things or the processing problems. Quick story here. I don't know if I've told you this already or not. I bring it up all the time, but it's just a good example of some various different things. I had an interpreter friend one time tell me that they were doing uh, they brought their client to do a psychological evaluation, and the test administrator, who was a psychologist or psychiatrist or something, he was giving a test. And one of the things that happens in intelligence testing is they'll say, um, describe this word, and they'll give a word and the person has to describe it, or sometimes, like, here are a few things that describe a thing, tell me what the word is, or something like that. And the word was velvet. And the interpreter spelled out the word velvet because in American Sign Language there's no sign for velvet, so they spelled it out. And afterwards, or maybe even they stopped the test in the middle, they said, well, the client got this one wrong or was trying to explain it, but they didn't really know what it was, because instead of having one sign for the word velvet, there was these VLVET, six letters. I had to count it out there. Six letters, and one thing in the brain is different than six things in the brain. Another example of that would be like, if you've ever heard the fact that the Eskimo people have like 15 or something different words for snow, and we just call it like snow, but they have cold snow and wet snow and I don't know, like the hard packed snow versus the light and fluffy snow. And they have all these different words. They see things in different nuance, which does that make us less intelligent when we're in a winter environment? So these questions of like, are we testing in a way that makes sense, that gets them information we want to get? And there's all kinds of different nuances there, which reduces the validity of tests. I think this is where some of your concerns about, are we really doing the right thing here? Are we testing the right things? Are we getting good results? Well, given those unique caveats and people's, I don't know, multicultural experience of the way science developed through a very different culture than we have today, maybe not. And there's really good concern or reason to question the validity of some tests based on that. So, well, I'm gonna let that one hang out, but I still don't think that's a reason to get rid of them or not use them or not think they're important or valuable for some things at least. Because remember, it's a matter of degrees. One thing that probably is going to be less relevant to most of us because we're probably not going to be doing a lot of intelligence testing. If you one of the part of the process, somebody mentioned this a while ago. One part of the testing process is if you have a very long test and people start to get fatigued at the end of it and they start just filling out whatever answers because I'm sick of this and I want to be done with it. Testing fatigue is one of those elements that can reduce the validity. So sometimes people will break up the test or they'll have to, I don't know, make sure they're well rested or whatever. I don't know. There's all kinds of ways you can correct for that, but test fatigue is a problem. In other words, the process of the test is just too long. One of the things you can do to account for that or sort of correct for it, I guess is a better word, is you can switch up the questions to make sure you don't leave important. Like if I said, I'm going to test all my depression questions at the beginning and all my anxiety questions at the after that, and then I'm going to do psychosis and schizophrenia and like all these other categories. By the time I get to the end, they're going to, if I have this test fatigue stuff, I'm not going to be answering correctly a whole bunch of categories of symptomology, right? So I'd have accurate results for depression, anxiety at the beginning, but not so much for psychosis or schizophrenia at the end. So what we do is we change the internal structure of the test so that these questions are mixed up. And there are scientific ways, and when you look at how tests are developed, you can sort of see like which ones are out of order and which ones need to be put in different places. And you can actually kind of go through and figure that out. There's a way to do that. So the internal structure, not something we really need to care about, but something to know that has been seen as a concern, and also there are ways to correct for it. So I'm going to skip this example. Although I do think it's funny. I was looking looking it up, and I found this term Borrelia burgdorferi, and sometimes will ask the class, "What does that mean?" And they're like, "I don't know." It just means Lyme's disease. It's one of those fancy Latin words or something for Lyme disease. Uh, in other words, the structure of the test is not really working because it's in a different language or something like that. So anyway, relationship to other variables is another problem. We won't get into that because this really gets into the scientific, or sorry, the more researchy components of test development. When we talk about correlations, which I'll get to in just a little bit here too, we kind of skipped over it previously. When we talk about correlations, we can see the strength of relationship between variables, also the strength of relationship between questions. It's one of the things you can do. You can use these fancy statistical tools, not software, but like a certain test process in order to determine if there's correlation between answers on tests. And so it's really complicated math. But essentially it says, are these questions good in the right, asked in the right way? Do they make sense together? Do they fit the construct? Is it irrelevant? And like it goes through all these kind of validity questions and asks that based on correlational data or relationship between questions and constructs and that kind of thing. So all of that kind of sort of fits this 3C model, this construct, content, and what was the other one? Criterion. We didn't even really talk about that one, but it sort of fits the way I was talking about construct. Kind of left it out on purpose because it just goes too deep into what I don't think we need to. But the other one we didn't talk about, and this is a relatively new development in how we're understanding validity, but the argument goes something like this. This is sort of changing in culture too, as we move from thinking, really emphasizing the importance of the scientific process, but now also recognizing the importance of systematic discrimination and processes that disadvantage some kinds of people in some ways. So the arguments goes like this. We have an ethical obligation to do right by our clients. Another way of saying that is we have a fiduciary responsibility to act in ways that are good for our clients. If we don't do that, or a test could do harm, then it's probably more ethical to not do that test. In other words, this test is trying to do something good. And remember, validity is the test trying to get at what it's supposed to be getting at? Well, it might get information, but it gets information that's going to harm the client. And if that's the case, then there's a consequence for even using the test. And that is kind of, I'm maybe not explaining this exactly well, but it's kind of a validity concern. Is it doing what it's supposed to be doing? Well, if we're supposed to be doing good to our clients and we're not, then the test is sort of invalidated by the fact that it does naughty things or does harm. That hopefully that makes a little bit of sense. So it's not only an ethical problem for some people, which it may be if that's the way you think, but it's also a scientific problem. In other words, we have this responsibility that we cannot fulfill even scientifically. And so there's some debate about that one, but it's a relatively new addition to this scientific conversation, not just an ethical one. But I'm going to leave that one out there and we can talk about it in class if we feel like we need to. Okay, so now we're going to get into some of the details. What you see on your screen, I'll give you kind of an example of it. We'll go back to our courtroom and crime scene analogy thing we were talking about earlier. But essentially, what we're doing is if we did all that fancy math and we come up with numbers to help quantify how much are we getting this right, how much is the test valid? Remember me saying you can reorder the structure of the questions and you can find out if there's irrelevant variance based on the way when the test is normed, people are responding to it. Well, there are numbers you can put to that stuff. And this, what you see up here, essentially relates to those numbers. Now, what you see here, it always is confusing to me because I'm going to show you another thing called the standard error of measurement, which has a different set of numbers. In one case, when we're talking about validity, a very high validity coefficient is above zero point 0.5, but a very uh, strong reliability number is above zero point 0.7. And so getting these numbers straight in your head can be a little bit confusing unless you're in it all the time. We probably, most of us in most of our work, are not going to be looking at these numbers all the time. So before I even explain what these are, I'm just going to say the best thing you can do is if you ever have to look through a test to find out if it's valid or strong, just Google this again and be like, okay, what was the validity? What's a high validity number? And then you'll come up to this because these numbers don't change. They're all over the internet. You can just reference them again. So if you're flipping through a test manual because your boss told you need to find a new thing, and you can always just go back and be like, is that a good number? I can't remember. Oh yeah, okay. Anything above zero point 0.5 is very high. So let's go down to the this chart here. I'm kind of standing in the way. I'll move for just a second. Let me explain it this way, and then I'll move again so you can kind of see. When you have a person who's committed a crime and they're going through the court process, if that person is guilty of a crime, you'd want to make sure that through the legal process and through both attorneys talking it out and the jury and all that stuff, there's a systematic process. And the reason is that you want to get it right. If they did the crime, you want them to have the consequence. If they didn't do it and they're innocent, you want to be able to find that out through the process of evidence discovery and all the whole thing to find out they're innocent and they shouldn't have a consequence like going to prison or whatever the thing is. So in other words, if they're guilty, you should find out. If they're not guilty, you should find out. And both of those are really good scenarios. However, sometimes the process doesn't really work, doesn't catch all those things. So sometimes a person might be guilty, but they're found to be through the judicial process, they're found to be innocent. In other words, a criminal goes free and they shouldn't, right? That's a bad scenario. In this example, somebody is innocent and then they go to prison because they were found to be, they were said to do something wrong. It's kind of like the witch hunt sort of thing. It's like you're a witch but they're really not, but they still get burned at the stake even though they did nothing wrong. So this is a problem. This is a problem. These two are what we're really shooting for here. Same thing with a test. If you have depression at some varying degree, you want that test to reflect that. That would be validity. If you don't have depression, you want the test to find out this person is not depressed. That's validity. However, if we get it wrong, that's not a good thing. Okay. So that's essentially sort of like a high level understanding of what we're really trying to do here and what these numbers reflect. I'm not going to go through whether how the math works out. All you have to know is sort of that example and then say, is it doing what it's supposed to be doing? Catching it if you have it, not catching it if you don't. And these numbers will tell you how much can I trust this? That's the big question that you get to ask yourself. Can I trust this information? If the validity number that you read in some manual or on some research paper is above zero point 0.5, that means you have very high confidence that this is measuring what it's supposed to be measuring. Somewhere between uh, zero point 0.4 and 0.49, it's still a high number. Between zero point 0.2 and 0.39, still, it's okay. And I would still use that test probably, but I'd be a little bit cautious about interpreting the results. And then below zero point 0.2, it's just, you shouldn't use it. Okay. Nobody's probably going to publish their test for sale. You might find research papers where somebody's sort of testing out their tool for the first time. Hopefully, doesn't always happen, but most of the time, the scientific process will catch that. Editors, peer reviewers, the community will say, okay, yep, the results are in, and this paper is published, and this test should not be used. And so most of you doing clinical work are not going to see those tests because of that systematic process to filter out this kind of stuff. If the scientists and the academics are doing what we're supposed to be doing, if the process works, and I say it works mostly, problems everywhere, right? We all get things wrong. But if it mostly works, and I believe it does, then you guys probably won't be introduced to things that are highly problematic. You're going to see things that are mostly okay to use. Now, something to be cautious about is knowing that some test developers are doing their own science and there is a incentive, like a capitalist incentive, not to sound, uh, well, I don't know what it sounds like, but not to sound weird about it, but if I want to sell a test, I have incentives to show that that test works. So what some people will do, and I'm again not going to go deep into this, it's just like if Google wants to find out if their new AI tool is a good one, if they take internal data that verifies that their tool is a good one, there's reason to be cautious about that. But if they make data publicly available and it's tested by third party people, like people will pay academics to then go in and do this science, even then there's a little bit of reason to be cautious about it because there's money involved. So in the scientific process, editors, scholars, that kind of thing, we really try to remove ourselves when we're doing pure science to come up with these numbers so that we're not influenced by conflicts of interest. And so there are processes for all of these things to be done well. And I think generally, if you ask me, should I trust it or should I not? I think you should trust the process. The more for those of you that want to go on to doc school or get more into this, there are ways to learn this process so you can tell whether it's good or not good. And the more people that do that, the more confidence we can have in stuff that clinicians get to use. I think it still works pretty good. And for the most part, if you see tests out there, I think you have more confidence than not that it's been through a process that says it's probably useful. The question is, in what context do you think it's useful for the people that you know and the way you're using it? That's a little harder question, but that's why we take practice, right? So, can we trust the science? I think so. And here's one way to do it. So, I'm going to keep moving on just for the sake of time because we're about halfway through and we're about at the 30-minute mark, just over. Let's switch our brains over from validity. Is it telling us true or correct results, the thing we're trying to understand? And are we getting consistent results? Another couple words here that are just kind of semantics, but are these results dependable? Can we reproduce these results in a similar way? So um, these used to be two separate lectures, and I probably should have taken out number two, so we'll just forget that one. But one thing you'll hear when people do tests is, oh, I could have done that better next time. Did anybody take like the ACT, SAT, GRE, one of those academic tests, and you're like, well, I was so anxious the night before that I didn't sleep very well, so I probably could have done better. Well, part of the scientific process is we take into account what are people like at their best and what's typical results. We sort of skimmed over that one in a previous lecture, but are we getting accurate results? That validity question. If a lot of us think if I took the test again, I could do better, right? So there's a thing that I'll show you that we've already kind of looked at, but we skipped over it called confidence intervals. That is essentially how much can I trust this number based on if I took the test again, it would fall within this range. So that's not exactly what confidence intervals, but you can think about it that way. Um, so there's probably more to say about that, but just for the sake of time, I'm going to skip over it. What I will say is that this idea of I took it once and then I could take it again and do better. You'll hear that from clients from time to time, especially when it comes to school counselors. And they're like getting back these academic results. Students are like, I didn't like my results, so I'll probably try again or something. And that's totally fine. Part of what you can do then is help them understand if you took it again, here's likely the range within which you'll fall. And so we'll talk about that in a sec here. So this idea of I got it wrong this time, or there's something in the process that isn't working, essentially what we're talking about is error in the process. If I have a headache and I didn't score well, I should have scored here, but I actually scored here. So this is how much that it was wrong about the process, or the got it wrong. And it can be wrong for all kinds of reasons. Okay. We're talking about reliability here, but essentially now we can take another step back, I guess, and say, how do we know how much this test is getting it wrong? So here we have a bunch of different kinds of error. I don't want to go through all these. I might pick and choose just a few things to say, but I don't want to go through all of them. But I want to, I'll talk about this equation, and then we'll just say there's a number that we can get to talk about the error, and there are ways that you can discuss this. So that's kind of what I want to focus on mostly. Not that you know the kinds of error, but how do you talk about how the test can get it wrong? Um, One of them is tests can change, performance can change over time. So if I took the test, didn't do well, maybe next time I'll come in without a headache or without anxiety and I'll do better. Or what if I study? Well, if I study, that's certainly going to change. Well, probably going to change your results on the test. So there's this thing called time sampling error. Sometimes people just tend to do better if they've taken something or with the passage of time. Um, Content sampling error, if well, I'll just skip over that one, but it's just another kind of error. We talked about that when we talked about the content of do I capture all the dogginess or not enough of it or something like that. So that's construct validity. It's related to it, but this is a slightly different thing, which again, who cares for now. Um, we talked about test fatigue and the quality of test items. The other one that I think is really important is test taker variables. Illness, lack of attention because of anxiety or sleep or ADHD or whatever. When tests are normed, what the process does is it takes into account all these extraneous variables, and it says based on people on their best day and their worst day, with one administration or two administrations, people who took it in the morning and people who took it at night. And we kind of give the test in all these different ways. And the more data that we have, the more administrations we have, the more these things sort of self-correct the process. So I'm trying to think of a better example, but maybe the best one I can think of is like if I shoot 10 arrows at a target, I might get one in the bullseye and a couple over here and a couple over here. But if I'm consistent, or if I'm a reliable shooter, I can actually shoot well over and over and over again, and I can hit that bullseye. What we'll start to see is a pattern. We'll see more of them hitting in the same spot and less of them that kind of go way off, right? So the more arrows we shoot or the more data we collect, the more we'll start to see patterns about where is this person typically shooting. Is it the small bullseye, the big bullseye? And, it gives us a better picture of how we shoot. It's sort of the same thing with tests. The more test administrations we give, the more, if we were to map out that data, it starts to look like that normal curve, and it accounts for things like these test taker variables. So if you say, well, I was anxious, and you're like, well, I'm comparing you to a whole bunch of other normal people that are anxious too. So that one really isn't a good argument for you could do better because everybody else is anxious and doing poorly too. You know what I mean? So those things get taken into account in test development. So we can figure out how much error there is in the process by doing that and figuring out all these other anxious people, but then the people who aren't anxious got this score, and so you could likely score that. So there's a little bit of error here. It's kind of generally how that works. And then test administration, standardized tests given in a non-standard way. I think that one's pretty self-explanatory. If you decide you're going to go off script and you're comparing not apples to apples now, but the way you're administering it to your client is different than other people, you might be giving them like little hunches, probably subconsciously, maybe intentionally, I don't know. But you might be giving them little hunches that help their performance a little bit more, which means that you're not really getting consistent results that can compare to other people. So the test administration, the reason for standardization is that we can get accurate measurements. That's the idea. Now let's go back to this equation because I didn't really explain that, and I think this is really important. When we look at a person's score, what we get to see, we don't really know if they were anxious the night before. We don't know if they have a headache. We don't know about how the test was developed. We don't know about any of that kind of stuff. But what we do know is we observe something. We have an observed score. Whenever we look at their raw score and T scores and all that kind of stuff, what we see is the observed score. But if I had a magic wand or a crystal ball or a God's eye view or whatever, and I could see all of those other things that are happening that influence the results to be higher or lower, if I could do that, I would know their true score, what they actually should get. If I could control for all that extra stuff, I would know exactly what they should have got, their one true score. But what I can see is the observed score. So everything between what I see and what actually happened, that's that measurement error here. So this just gives it kind of like a, I've described it in several different ways, but this gives it kind of like a mathematical way of understanding that. So, question for us is, how do we know? Uh, which I guess we can't answer that on this slide, but I'm going to give you a few other things to know that'll help us get to that answer. How do we find out? Part of it is we have to know what we're looking for. Okay. Whenever we look through a test development manual or we look through a scientific study about a test, like if I look up the Beck suppression inventory, you're not going to find a manual because it's just the same questions on the internet. What you can easily find are dozens, if not hundreds and hundreds of studies using the Beck's depression inventory with different populations in different places on the earth and all kinds of stuff. And what we want to look for is some reliability numbers, right? Well, how do we know what to look for? Reliability is always, always, always going to be written with this tiny lowercase italicized r. Anytime I see that lowercase italicized r, I'm looking at reliability, kind of. There's another thing that uses that R, but most of the time you're going to see it written. And I'll show you an example if I can. You're going to see that little tiny italicized R equals 0.83. And it won't always say, here is the reliability number and you should trust this. It's going to say the reliability numbers were, or the alpha numbers or coefficients or something like that. And it's going to have that little R. Whether you know what coefficients or alpha numbers or any of that kind of stuff is, if you see the R, you can expect to see a point something number. And then you can look at what we're going to show in just a second here, this, and say, oh, there's my standard of error. I know if it's this number, that means it's very good. Okay, so we'll come back to this in a second. Um, the second bullet point here, it's not something we need to focus on, but there are different ways of testing this kind of thing, reliability. You can give a test at one point and then give it again. We've talked about that, like get a baseline score and then another score. And if they're equal, we can pretty much say, oh, this seems to be accurate. That's what we do in our heads anyway. If they're not equal, we ask ourselves questions. Is it because they've learned something new or time has passed? Or is there any other explanation for that? We do that kind of naturally in our heads, but this is one of the ways that we can systematically test reliability. Sometimes there are alternate forms of tests, and we can find out that way. If I give this same person two different forms of the same exact test and they score the same result, it increases the reliability, right? There's one called the Wide Range Achievement Test, and it gets pretty widely used, or called the WRAT, WRAT, and it uses a blue form and a green form, and that's how we can test to find out, is this actually is it reliable? The test reliable? In practice, mostly what you do is you have a room full of people and you give some green, some blue, and then that's just helps the administration. But if I wanted to, and this I think has been done, I could give one person the two different versions and find out how they score, and then say, yep, they're both good. The person's scoring the same on both tests, so they're both probably useful. We'll skip over the internal consistency, but the other big one, and I think this is probably fruit for a conversation, so make note of this if you're curious about this, but it's inter-rater reliability. If I have two clinicians, one on this side of town, one on that side of town, both of them have the same skill level, and they have the same client because the client goes from one for an evaluation, then goes across town to the other, I'm going to get some different results, right? But that's not really super ideal because if you go to one counselor and they say, well, you have bipolar 2, and the other go to the other counselor and they're like, no, you don't. You have PTSD, whatever the thing is. That doesn't really happen. It's sort of a silly example, um, but if you did that, what we're talking about here is inter-rater unreliability, right? The person has some condition or has something going on, but if the raters are different, then who's to know who to trust? This is another one of those arguments for if we standardize the tests and we have a common list of criteria, the DSM, then we can start to say, well, we're looking at the same symptoms. We have the same test and it's given in the same way. So we should come up with the same results. This is one of the reasons I think, and I have never had this conversation, so I'm kind of making stuff up a little bit here, but it's one of the reasons I think historically people have relied on these test taking processes, why people who use tests like psychologists are like, well, we all learn how to do them the same way to correct for that kind of thing. And one of the major flaws with counseling and social work and marriage and family therapy is that we're not talking about apples to apples. We're coming from different perspectives with different theoretical orientations, and it reduces the reliability of those outcomes if we're trying to do something like diagnosis. Now, that's not saying that we should focus on that and it says all diagnoses are bad because of it. That's not it at all. There's a whole bunch more to this conversation than that. But nevertheless, there is an argument to be made for standardization and scientifically sound testing materials, and why I think we would be remiss if we got rid of them and didn't use them at all. So, food for thought. You guys take it and do what you want with that, I guess. Um, let's see. I think I'm going to skip over the rest of this as we've kind of already touched on most of that. Um, Probably going to skip over most of this. We're talking about the specific kinds of uh, methods for estimating error. But again, I don't think we really need to know that. Most of us will think about test, retest, and the length of time between administrations or understanding the construct. One of the questions that's come up in class is this GAD-7 or this PHQ, are these testing exactly the symptoms that are in the DSM, or are they testing other parts of the construct that doesn't really fit the DSM exactly? And so, what we want to do is we want to know the DSM well enough and then know what we understand about depression, how it shows up with different kinds of people or anxiety or whatever the condition is, so that we have a fuller picture of these constructs. And if you do, when you get to that place where you can evaluate, like, there's the test result, here's what the DSM said, now I can make a good, sound, experienced clinical judgment about the diagnosis or the construct of whatever ailment this person has. Um, so that's kind of there's pros and cons there, but it's why I'm talking about it a little bit is to say we're probably doing these things naturally, trying to correct for error, but all of us in the class are like, oh, I feel like I don't know all those things, so I'm going to make a lot of mistakes. And I'm like, yeah, but that doesn't mean we shouldn't be doing them and working towards more understanding, more knowledge, more experience. Because at some point, hopefully, if all of you learn a little bit about these different things, the DSM, and even though you may not like it, you may not like these testing tools, the DSM, the medical process, the whatever. If you know it, then you can account for it and understand it thoroughly, even if you don't think it's a good thing. Sort of like the devil you know is better than the devil you don't. Here I'm trying to make an argument for here's why you need to know the devil, the DSM, and the insurance companies. No, I'm kidding. It's not; those aren't the bad guys. But we do need to, if we're going to have reliable results, we need to understand and speak common language with our peers. So, enough said for now. I kind of explained this alternate forms thing probably well enough. And the internal consistency is sort of talked about that. The one thing I'll mention here is this number two. Well, two things actually. This number two, you'll hear sometimes these terms like Spearman Brown, split half, Cooter Richardson. All these are just fancy statistical processes, or not. They're not really equations per se, but it's a mathematical way of handling different kinds of information. I kind of mentioned that a few weeks ago, regarding the certain kind of data that you're collecting. you have to have different tools for different kinds of reliability in different situations. So you'll see those terms sometimes and you'll just say that has something to do with reliability. Don't really have to memorize that, although I think you will find some questions periodically on like the NC. I think there's one on your stats quiz, maybe even about the Spearman Brown. Um, I couldn't tell you what it is right now if you held me at, I don't know, finger point or something. I won't say gun point. Too triggering. Haha. Just kidding. Bad pun. Um, the one you will see most often, you'll see it in research papers. You'll see it in testing manuals. Is this one called Cronbach's Alpha? Remember when I said that small little italicized R? It means reliability. It's also the one thing I didn't tell you because I didn't want to complicate this for you, but it's also uh, what gets used for correlation. So a little complicated and confusing. But when you see Cronbach's alpha, sometimes it'll say the Cronbach score was, or the alpha score was, or you'll just see this little symbol that it's just the Greek letter alpha. If you see that, you know you're talking about a certain kind of data, which is nominal data, which means words. Um, I like, dislike, or strongly dislike, or whatever, those kind of things. Because we're on this sort of on those Likert scale kind of ways of measuring numbers, or whatever, which we do a lot in this field. Cronbach's alpha means reliability. Okay, probably enough, but really, really important. So I need to sit on it for just a second here. Now, we've already talked about interrelated reliability. Now, reliability coefficients are always measured between 0 and 1. Correlations, the direction and the strength of correlations are between -1 and 1. Remember that from the day before? If it's negative, we have an inverse relationship. One goes up, the other goes down. If it's a positive correlation, 0.80, whatever, that means as I give more treatments, person gets better. So the directionality of the variables both go up. Okay, so that's correlation. Reliability coefficients are always measured between 0 and 1. In other words, 0, very very unreliable. Don't use this test. 1, there is 100% accuracy between one administration or the next one, or one rater and the other rater, or whatever. It's never 1, but it can be very close. If you see, and this goes down to this little paragraph here, if you see that small little italicized R, and it says we have a score of 0.95, essentially in mathematical terms or statistical terms, what we mean is 95% of the difference or the variation between test scores. So first administration, second administration, first form, second form. If there's a difference, that is our measurement error. And if we have 95% of the variation between those scores is a real difference, that means there's 5% error. Okay. So when we say there's a Cronbach alpha score of 0.8, it means 20%. I'm going to get this wrong, probably the way I say it, but 20% is the error in the process. Okay. There's another more statistically accurate way of saying that, but I'm going to leave that out for right now. So, what does that all mean? When we are trying to figure out how much does this process mess it up or get it wrong? Well, when we use things like the statistical tools like Cronbach's alpha scores and the way of getting that to that number, we're figuring out how much does this test get it wrong. And if I have an alpha score of 0.95, that means 5% is the standard error. Okay. So there's a lot more to that, and we could explain it more in statistical terms, but I think you don't really need to know that. Because the big question, going all the way back to the beginning, we're almost an hour in here, and we're wondering, can I trust this tool? Well, if you go look at some testing manual or some research paper and it says the coefficient, the alpha coefficients, or the Cronbach's number or something like that is 0.8, well, the question we're asking ourselves is that good, and can I trust this? So here's our answer to that, finally, after 3 weeks and another hour of learning. Another way of saying that is if I took the same test over and over and over again, or multiple versions of that test, or I went to a bunch of different counselors to correct for this reliability challenge, it's going to get it wrong sometimes. But how much can it get it wrong and me still believe in the results, right? So here's our measurement. If the reliability coefficient is 0.9. It's very high, and we can trust that 90% of the variability of blah, 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 all that statistical stuff. Believe it, trust it, that's okay. If it's 0.8 to 0.9, it's high. If it's 0.7, it's acceptable. Below that, probably look elsewhere. Probably don't use that test because there's too much reliability. Another way of saying that, and this doesn't really get tested, but if I went to one counselor and then to another counselor and I tested the reliability between those two, if I found out that my reliability coefficients were lower than 0.7, I probably would say I can't trust any of these results, which is problematic, right? Which is why there's not a whole lot of science on it because people aren't testing that, right? However, what you need to know and what you probably want to sort of put a pin in it in your head or, write this down in your notebook is that zero point 0.7 is acceptable. Now, when we looked at the validity numbers before, zero point 0.5 was very high. Here, what we see is zero point 0.9 is very high. So let's actually go back there really quick. Right here, acceptable is anything higher than 0.2. And here it's anything higher than what I would argue is 0.7. Now, how do you remember this? You Google it, or you ask uh, Perplexity or ChatGPT or Copilot or Gemini or what. Just ask the AI, and it'll say, "Is this an acceptable number based on statistical standards?" And they'll say 0.7 or above. Yes, it is acceptable, and like that's probably enough. I don't know if I'm not at a place to sort of endorse AI use for that yet, but that's how you find information, and you can just reference this. You don't need to memorize it. For the purposes of testing, you probably want to put that one in your memory bank that a standard error of measurement or reliability coefficient or Cronbach's alpha, anything above zero point 0.7 is probably pretty good. I have not looked at a test that is being sold with anything lower than 7 and seen it continuing to be sold. That's why I said in the beginning, where you can kind of trust the process to say if it's available out there, it's probably okay. That doesn't mean that you don't still need to do your due diligence to look for it and to find that answer, but uh, trust the process is kind of the answer that I have. You decide if you want to fight me on that because we can talk about it in class. That's not really a fight. It's just a friendly debate about how much we should trust, which is a good thing to do. Okay. Uh, if you want this link right here, this was a friend of mine who I went to school with who wrote a really, really good paper, and it has a bunch of this kind of stuff in there. If you want to go dig through an interesting scientific paper, I don't even remember what this is about. I'm going to click on it. If you want to look at a really interesting scientific paper, and try and dig through some of the hardcore science, if you really want to know this stuff, this is a pretty cool one. Oh no, this isn't the one from my friend. Here, let me pull this over and see if I can show you. This is a different one. This is the validity and reliability of the PHQ. So I'm just going to go right down here to the abstract. No, where was that number? Oh, here we go. Here are the results. What is the reliability, or in other words, can I trust the PHQ? The Cronbach's alpha coefficient of the PHQ is 0.83. Okay. That's probably enough for me to know. There's a bunch of other science here and a bunch of other statistics. But if I don't know what all that means, what I can start saying is I could probably test. I know how to look for whether a test is a good one. I look for this Cronbach's alpha, and this is just a paper that's out there available on the internet. And here's the alpha score. Then I go back to here and I say, is 0.8, what was it again? 0.8839, so 0.84. Is that acceptable? That's actually high reliability, which means there's 15% error. So 15%, this is not technically accurate, but close. 15% of the time, it's going to get something wrong. That's, again, if you ask a scientist, they're going to be like, that's not what we're talking about here. And it's not, but for all intents and purposes, for clinical usage, you can say 15% of the time, we're probably going to get it wrong. That's still pretty high, right? It still means that you can trust the results. Okay, if you want to see another example for the 16 PF or the 16 personality factors, we'll go through that one again later in class. I'll talk about that when we get to personality inventories. But on page 321, there's an example of talking about the measurement error in that test. So I think we are almost done. There's one more thing, and I'm right up at an hour, but this one is an important one. And then I'll show you some examples of this in class. This gets a little technical. and I already alluded to this at the very beginning of this lecture about confidence intervals. When we bring up this question of trust, can I trust this? And I talk about validity and reliability, and I say there's a bunch of science and math and all kinds of blah, blah, blah. Can we trust it? I keep bringing up that question because that's what this is really about. Are these results useful to me and can I believe in them? The confidence interval says if I do some math, I take that standard error and I say we can calculate what the standard of error is and how much error in this process. If my alpha coefficient is 0.84, that tells me something of how much error. In other words, if I do some math and say, if I took this test again, how much, or maybe if it's not if I take it again, but how much is it likely getting it wrong? And I guess if I were to take it again, what would my what would my score fall between? That's what we're really trying to find out here. It's an interval between the high side and the low side. So if I take my observed score, remember that word we used earlier? The true score is probably somewhere between here and here because I know what the error is, so I can measure how far away from my observed score I probably am. And I'll show you what this looks like. I'm not going to go through all of this, the language here, because it really doesn't matter. But what you can say is, and we'll look at some of these examples in class, what you can say is if you took this test again, you'd probably not score higher than X, right? If I scored a 25 on my ACT or an 18 or whatever it is, and they say, "Oh, it's because I had a headache and oh, I was so anxious, so I could score 30. I swear I could. I know I have it in me." And you're like, "Well, I can say with 99% confidence, and this is, oh crap, this is how we look at this. It's usually either 99 or 95. I can say with 99% confidence that you scored a 18, you're not going to get below, or you're not going to get above a 23, based on how much error I know there was in the process. If you study, you probably could, but if you just took it again tomorrow, you're not going to score higher than that, which is also why test administrators say you got to wait 6 months or you got to wait 3 months or whatever after you take one test because we need you to go study. If you just take it again now, you're not going to get much higher than that. So there's reasons for why there's that gap period between administrations. I'll go through some examples of this, but I will pull up just one really briefly that we'll talk about in class. Oh my gosh, that's so gross looking. But do you remember this when we brought this up in class? Here's the key math scores. I'm recording this lecture before tonight's first lecture of understanding assessment scores. So tonight we'll see this. It'll feel like last night or the night before, whenever in class in lecture 2 of our mini series, we talked about these confidence intervals or we breezed over them. Essentially what I'm seeing here is I took my raw score and I turned it into this thing called a scaled score. Now, we don't care about what the scale score is. We haven't really looked at that before, but now it all of a sudden matters a little bit because I could say the scaled score is 6. And if I have a confidence interval based on how much error I know is in the process mathematically, I can say this person likely would not score between a 5 and a 7. Now, what we don't have is we don't know what that grade equivalent or what that age equivalent would be. In other words, if I took it again, I might score like an 8-year-old or I might score like a second grader. And that's true, we just don't really know that. But what we can say is here's how much we can be confident in the results. Now, usually, down here at the bottom somewhere, there is something about telling us how confident we can be. And in this case, I told you it's usually 99 or 95. Well, in this case, it's 90. So 90% confident that if you took this test again on this numeration scale, you would not score any higher than a 7, but you probably also wouldn't score any lower than a 5. These kind of conversations I'm not having with clients. I don't have these very often, but it is important that I do because sometimes I've heard of scenarios of people really being pushed on whether this test is a good test. And it usually happens to school counselors in my experience, or if you're doing forensic work and someone's nitpicking about something, but some attorney is nitpicking. But typically there's some giving you some information about how much confidence. 90% confident that if we took the test again, they'd score between 5 and 7 on this numeration subscale. Okay. If this number is really wide, that means there's more error in the process. And so we'd have a lot more variance in that score, which means that they could score much higher or much lower. We just don't know. If the score is a lot closer to the scale score, then we are um, a lot more confident that this is very reliable score and we can kind of trust it. That's what we're trying to do here is to put this into common nomenclature is just we can trust and have more confidence in the process that the math is probably correct, valid, and reliable. Okay. So that's kind of my mic drop moment. That's where I'm going to stop talking about this, but this is the end of the lecture too. So one thing you can think about as you're planning on coming into class is come with your questions. I'm going to get below my captions. Come with your questions about what makes sense and what doesn't, but probably even more importantly, now that you've gone through this, we've talked about assessment scores, we've looked at some different reports and results, and we'll continue to do some more probably as we go through the class. Has your opinion changed about how much you trust the process? Or depending on whether it's changed or not, what are you considering about the things you think are working and the things you think are not working with the formal assessment process? With the informal process, what are the pros and cons to that too? Because if you're like, I'm going to throw this science stuff out because this is really about this artistic, ethereal relationship that we have full of energy between people, and I buy into that stuff. I love it. But what are the limitations of it? What are the pros and cons of that versus pros and cons of this quantitative stuff too? That's really what I think the conversation that might be interesting to have. If you have something else that's interesting to you too, great. Bring it in, we'll talk about it. But just some food for thought. Okay, that's it for me. I will see you guys in class.